Did the recording. Yeah. So during the course of fourth week, I think three lectures were given. Three lectures were uploaded on the platform, and we mainly the topics which were covered were based on free surfaces, and also there is also one session which was explaining the uh, a very brief introduction or a bird's eye view to photoelasticity, how it works, and what are the different principles involved in it. And then we have gone to the another facet of the course, which is like till now we discussed uh, stresses. So now we are entering into another facet of this course, like stress, and we have strain. So stress, the thing, the introduction and various uh, small things were discussed, like how strain tensor is derived and a rotation tensor, all these things. So we'll just look at a few questions. So let's see this first. Let's see this picture. This is a photoelasticity. Photo. This is this picture. The same picture you might have seen in the photoelasticity lecture. So here we are looking at the fringes when uniaxial load is applied in this direction, basically uniaxially loaded in the uh, perpendicular direction like this. This plate is loaded like this in y direction. So, and there is a point given, and you have to find out what is uh, the stress tensor on this uh, plane. So let's see if this, if I take this point. So basically, in this question, we have to find out what are the zero stress components in this stress tensor at T. So if I take a small element like this on this boundary, which is not loaded here. So here I can take a suitable reference coordinate system can be here it is better to take a polar coordinate system because it is like a circular hole. So r theta. So if I in this because this is a two-dimensional thing, I'm just writing a two-dimensional tensor. So two-dimensional tensor for a circular coordinate or a polar coordinate system can be written like this: sigma theta and sigma theta, sigma r, sigma theta. So here, if I take this, this will be my sigma theta theta, because as theta changes, this changes, and this is sigma r, and we have shear, which is sigma r theta. So shear cannot cross a free surface, so that's why shear component will be 0, sigma theta will be 0, and we also have sigma rr, that is also uh, there is a free surface and the boundary is not loaded. That's why this also becomes 0. So this this sorry, sigma theta will be there, and this will be there, and the stress tensor will look like this for this. So sigma r theta and sigma r will be 0. So, and the next thing which we are going to see is we have to identify what are the points, and for this loaded element, identify the point where stress tensor is 0. So you can see this when we see in yes, sir. When we look at the photoelastic fringes, so wherever there are like black spots in the picture, like you can say that this is 0. I hope you are able to hear. Yeah. So wherever there are black spots, that is A. Here we have C, and we have D, and here we have F. Here we have G, I, J, and L. So all this A, C, D, F, G, I, J, L, all these points have zero stress tensor, because in a corner, if I take a small element at a corner, you can see that anyway shear will be 0, and you cannot have uh, normal components also, because there is a free boundary. So that's why entire stress tensor will be 0. So at corners we have stress tensor as 0. In There are some cases like there is a if there is a re-entrant corner. Uh, let's see at this example. We have uh, this uh, a bar or a plate, small plate like this. It is loaded this direction, and let's say we have like a wedge like this, and if we take a point at this, you can see we have learned like there is no shear force here because this is a free surface, and there is also no normal stress. That's why stress tensor to take surface along AB surface, or surface along, or element along BC surface. So stress tensor will be 0. But we have, but if we have our corner like this, where it's not like a wedge shape. This is more like a fillet, and this is like a wedge. So here, if you take a point B, this is called a reentrant corner, and here the stresses will be very high, and stress tensor is not 0 here. Very high, and you can say that stresses are singular, very high. Stress tensor is a not 0 here at this point. Next, let's solve a problem. So the question goes like this: a differential element of material point is subjected to a plane state of strain, which is given by epsilon is equals to minus 350, 200, 0 to 200, 80, 0, 0, 0, 0 microstar. First, we have to find out the value of first invariant. So this exercise we have done for the strains to stresses also in the last session, and similar thing we are going to do here. Value of the first invariant is given in microscope. Mic yeah. Oops. So we know that value of the first invariant is the sum of principal diagonal elements in the tensor. Here we have epsilon xx, epsilon yy plus epsilon zz. So epsilon xx is minus 350 plus epsilon yy is 80 and epsilon zz is 6. So we have J1 is which is 2 minus 270. This is the value of first invariant. Next we have to find out the value of second invariant. J2 in 10 to the power of minus 2 epsilon. So we have to be careful about the micros. Here earlier the units were microstring and here it is 10 to the power of minus 2. So let's see how it goes. So the second invariant is basically minors of the principal diagonal elements like epsilon y, epsilon z, epsilon yz, sum of minors of the principal diagonal plus epsilon xx, epsilon zz, epsilon xz, epsilon zx plus epsilon xx, epsilon yy, epsilon xy, epsilon yx. Here we have epsilon yy is 80 and 0, 0, 0, and we have epsilon xx is minus 350, 0, 0, 0. Z components are 0 anyway, this is a plane strain test, and we have epsilon xx as minus 350, 80, 200 and 200. So the first two thing determinants are anyway zero, and I have left with this minus 350 into 80 minus 200 square. So J2 will lead me to minus 68,000. This is actually minus 12. I hope I'm doing this. Yeah, my first two. Okay, let's uh, take this as this one first. We can convert this into uh, 10 to the power of minus 12 only. Like just use 10 to the power. Yeah. So this is the second invariant. Coming to the next, we have to determine the value of third invariant. The third invariant A3 is nothing but the determinant of the matrix. And the determinant of the matrix is can be given like this. Here we have minus 350, 200, 200, 80, 0, 0. So minus 350 into this whole part will be 0, minus 200 into again I will have 0 everything. I don't need to do the calculation. And 0 into anything is 0. So the determinant of this whole strain tensor is. Now I have to find out the maximum principal stress. So we know that by finding out the eigenvalue or writing uh, this equation, determinant of this should be equals to 0. Then we can find out the eigenvalues. or simply I can write this like this. It's K1 into lambda square plus K2 into lambda plus minus K3. I solve this cubic equation. If I simplify this, I'll get this cubic equation. And if I solve this, I'll get the three eigenvalues, which are the three principal states. So I have J1, which is minus 270, minus and minus leaves me to 270. And J2, I have minus 68,000. And I have J3 is 0. Yeah. So if I solve this equation, so and using a calculator, I hope you do the same. I have three lambda values. First is 158.64. Second one is minus 428.64. And the third is 0. So this is the smallest. So I'll take this as epsilon 3, and this is the highest at epsilon 1, and this is the intermediate one. So this is the maximum principal strain, maximum, and this is the minimum principal strain which we have. Yeah. Okay. So this is how it is similar to stresses, how we have find out principal stresses. Finding out the principal strains using a strain tensor also involves finding out the eigenvalues of the strain tensor. Next, we move on to the next question. The next question, uh, uh, displacement field is given, and which is x square plus x plus y square I cap plus 2x plus y square j cap, and this is entirely multiplied by 10 power 6, and XYR coordinates are in meters. Okay. So the first question in this part is to find out the normal stress, find out the normal strain as mu epsilon, which is micro strain in the x direction, which is epsilon xx at point E, which is uncontrolled. So any displacement field uh, which will be given can be divided like this. The x component will take it as u, and the y component of the displacement field will take it as j, and the z component we generally take it as w. So these are some standard notation. Uh, you find this in various books, and these are mostly consistent u, v, and w. So u is the displacement component in x, y, v is in y, v is in y coordinate, and w is the displacement in z coordinate. So we have this displacement field. From that, we have to find out the normal strain in x direction. So normal strain in x direction is basically dou u by dou x. So we have here u as x plus y square, and that is already given in given as 10 to the power minus 6. That I am taking it as my question. So dou u by dou x is 1, and dou the other part, because this is a partial differentiation, so differentiation of I square itself. So simply I have for the normal strain as 1 for this displacement uh, field in x direction, regardless of the point. For every point, this is the normal strain in x direction. Next, we go to the we go to determine the value of normal strain in y direction, which is epsilon y at the same point. And here we have epsilon y. Epsilon y I can write like this. So epsilon y is dou v by dou y. So we have v here. This also you have to find out in microscope. So v is 2x plus y square, 2x plus y square, right? Microstrain. So differentiation of x component or whatever the x terms are is 0, and y I can write like this. So this is epsilon y, right? And because it is present, we have to find out at point 1 comma 2. So we have only y here. I'm just substituting the y coordinate of the point, which is 2, and I get the normal strain as 4 microstrain. This is the normal strain in y direction. Next, we go to find out the value of engineering shear strain. Engineering shear strain. in mu epsilon, mu strain or micro strain, whatever, at the same point 1 comma 2. So the engineering strain can be given as gamma xy. You can write it like this. I hope you have watched the lectures. It is dou u by dou y plus dou v by dou x. So this is the engineering strain, gamma xy. If we take epsilon xy, that is half of this. That we write in the tensor, strain tensor, epsilon xy. But this is the value of engineering strain. So dou u by dou y, I can just substitute u value here, which is x plus y square dou y plus v is 2x plus y square dou x. I'll get 2y plus 2. So if I substitute 2 plus 2, y coordinate is 2 here for the point. So I'll get 6 across strain. Yeah, this is the value of engineering shear strain at this point 1 comma 2. Next, we have to find out uh, we have to determine the value of normal strain. Question. Let's see the question. Value of normal strain. Value of normal strain as microstrain along 30 degrees to the x-axis at a point. So previously we have find out the uh, x in x and y directions, whatever the strains, and I can write this stress tensor like this. I'm just using a two-dimensional tensor because this is uh, displacement field is in 2 dimensions, so I don't need to take a 3 dimensional case here. So I have uh, epsilon xx, which is 1, epsilon y 4, and gamma xy we have got 6, but we have epsilon xy, which is half of the engineering strain. So this is the strain tensor. So here we want to find out the uh, uh, value of this value of the strains along 30 degrees. So this is basically coordinate transformation. So you have strains on this epsilon xx y, but he is asking there is a plane uh, which is making an angle 30 degrees with respect to the x-axis. So for this we have to find out. So this is the plane 30 degrees with respect to x. Easier to write like this. So basically I can do a coordinate transformation. So I hope we all know how coordinate transformations work. Like we have coordinate initial coordinate system like this, x, y, generally suitable to be written in bold or capital letters. So I rotate this coordinate system with respect to x-axis and angle theta. So here and text this is it's like a that can be written as can be taken as cos theta or I can simply instead of doing messing up things I can write like this cos theta x minus sin theta plus sin theta. Yeah, cos 90 minus theta, which is basically sin theta y I can write like this. So minus cos theta sorry, minus sin theta x plus cos theta. So this is the coordinate system. This is the transformation matrix. For a tens, this is for a vector. For a tensor, I can take like this Q transpose epsilon equal Q cos theta minus cos theta sin theta minus cos theta. This is whatever we have got 1, 3, 3, 4. This is basically Q transpose of cos theta. So cos theta is the angle given is 30 cos cos 30 is root 3 by 2. Sin 30 is 1 by 2 minus 1 by 2 and 2 by 2. Just of like this. Hmm. Just making sure I'm not getting the notation wrong. So this disturbance not too much.
87% of IT professionals believe that APIs are crucial.
International education opens the door to endless opportunities, but these opportunities shouldn't be overwhelming.
Swayam Prabha. Digital India. Educated India. Swayam Prabha. Digital India. Educated India.
I have now our focus of it. Forces different planes equal to sigma xx nx plus tau yx ny plus tau zx nz. And in the epsilon xy, not gamma xy. That's the only distinction that you have to make. And you have to remain correctly. You can have cos squared theta plus epsilon yy
Yeah. Six. Or you just take this in epsilon xx form, and I'll write these equations because these were given in the lecture directly. So you can write this like this also, or you can do this. You can directly use this stress transformation now. Was directly because this will be easier as this was given in the lecture. I don't want to give a new perspective. I have given it, but this is the same thing if I take epsilon xx, epsilon yy strain tensor and multiply. These are the things which are get uh, for the transform coordinates. By 2 sine 2 theta plus epsilon xy cos 2 theta epsilon yy sin square theta plus epsilon yy cos square theta epsilon xy sin 2 theta. So epsilon xx is 1 cos square 30 and epsilon yy is x square epsilon yy we have 4, yeah. If it has 4 sin square theta sin square theta is 30 again plus epsilon xy here that is 3 sin 2 theta and that is sin 60. So I have I calculate this. Let's see what we get. Cos square 30 cos square plus 4 into 30 square plus 3 into sin 60. Get epsilon xx as 4.348. Let's see what I get for epsilon y for this transform coordinate system. Again, we will use this and sin square 30 plus 4 cos square 30 and minus 3 sin 60. Just calculate. So we get epsilon y by 0.52 something like this. Now epsilon shear strain, epsilon y cap x cap or x cap y cap or whatever. Y dash x dash y dash is 1 minus 4 divided by 2 into sine 60 plus epsilon xy. Epsilon xy is basically we got 3 in cos 2 theta. Cos 2 theta is here 60. So if I get this is minus 3 3 by 2 sine 60 plus 3 cos 60. Yeah. 3 by 2 sine 60 plus 3 cos 60. I get I cap as 2.79. So this is how we get this value of strains on the plane, which is question was we have to find out the value of normal strain and along along 30 degrees to its axis. So we find out this, and along 30 degrees to its axis, this is the normal, and this is epsilon x dash, and the value of this was we found out 30 degrees. And the other values also we have found out. Shear and also the normal stress along the other direction, other perpendicular direction. Shear also has been found. Yeah, this is how the strain transformation works. Next, we have to find out the trace of the trace means simply sum of the diagonal elements, principal diagonal elements, sum of the rotation tensor for this displacement. So for any displacement field, let's say I'll take this as a displacement field is generally taken as capital U, and this various components can be given like this UV, UVW along the various directions, components of the displacement field along the various directions, and we have the deformation grade, displacement gradient like this. So you by rho x, so you by rho y, so you okay, also like this. Okay. Rho w by rho x and rho w by rho y. So since in this course we only deal mostly with 2D systems, plane strain cases, just take this out. Get rho v by rho x, rho u by rho y, rho v by rho x, rho v by rho y. So we have seen in the class that professor has explained like how we convert this into sum of displacement gradient into a strain tensor and a rotation tensor. So this is basically taking sum of this is basically we divide it like this. Any matrix, I think you have studied this in linear algebra. Any matrix can be decomposed like this into some of a symmetric and a skew symmetric matrix decomposed. So this is basically our strain tensor. If you look, this gives our strain tensor. Yx and this will give us the rotation tensor. So in the rotation tensor, always the diagonal elements are 0. So sum of the diagonal elements will be 0 here. So no need to find out what to do. No need to do any calculations here. In the rotation tensor, the diagonal elements are 0. That's why sum of this or the trace of this uh, rotation tensor is 0. This is the rotation tensor. This is the strain tensor. Yeah. Next, we will move on to this question, a very lengthy and comprehensive one. So here we have, let's say, uh, this is an rubber pad. This is a rubber pad, and it looks like this. Initially, it was like this, and after it undergoes distortion, the shape of it changes like this. So let's say initially the points or the corners of this pad will be A, B, C, and D, and after the distortion, can write like A dash, this is B dash, and this is C dash, and this is D dash. And the dimensions look like this. This, the value of this is 0.5 mm, and the value of this is 0.75. So first we have to find the change in length of side AD in n power in the rubber due to the distortion which is. Let's check. Meanwhile, I'll just check the questions in the assignment so that I don't repeat the questions. Hi, Kishore.
Yes. Good evening.
Yeah, yeah, good evening. I've joined late. Nobody has joined today.
I went outside some of the results. So
Okay, okay. I'll just explain, yeah,
yeah.
what we are doing. Just give me a minute. Okay. So I'll just we'll go through this. We'll go to through this question. So there is a rubber pad, and after distortion and before distortion, this is the shape of it, and the dimensions and the displacements which it undergoes, various points undergoes, are given. So we have to find out first the length of the side AD in this the first question is this. So in order to find out the length of this side, uh, change in length of the side, which is first we have to find out this the length of the changed side, which is A dash D dash. Here this green line A dash D dash, which is nothing but this forms an equilateral triangle. I have root of 20 square plus 0.75 square minus, if I do this, this is okay. First I'll find out AD. So AD is the hypotenuse here. You know 0.75 and 20. Simply I'll get 20 square plus 0.75 square. Yeah. So this is the length of the changed side AD, 20.014. It goes like this, 0.5 something. So change in length of AD, change in length of AD can be given as the change length minus the original length, 20.014057 minus 20 something, get change in length of the side AD, 0.145, like this. So because I have to find out this in 10 to the power of minus 3 mm, so I'll just write it like 0.01, sorry, uh, write it like this. This is for so 14.057 to 10 to the power of minus 3. So this is the answer, change in length of the side AD. So next we have to find out change in length of side AB. Same in this like this 10 into 10 power of minus 3 thing. So here also we have to find out, first we have to find out the line length of the changed length, which is A dash B dash, and similarly it also forms a equilateral triangle, sorry, right angle triangle. So root over 15 square plus 0.5 square will give me the side hypotenuse or the changed length of the side AB. And it gives me 15.0083102. So change in length of side AB can be given as change the length minus the original length 15.00833 something minus 15. I'll get 8.3310 something into 10 to the power of minus 3. So this is the change in length of side AB. Now we have to find out what is the normal strain. This is the change in length, and change in length is fine, but we have to find out the normal strain along AD in the rubber due to the distortion. So normal strain along AD in into 10 power of minus 4 mm per mm format due to distortion. So normal strain can be given as change in length by original length. So change in length in AB is 14.057 into 10 to the power of minus 3 divided by AD, which is 20. $14.07 divided by 20. So normal strain can be given as 7.0258 into 10 to the power of minus 4. So normal strain is basically change in length by original. Similarly, I have to find out normal strain along AD, along AB. Same like this into 10 to the power of minus 4 mm per mm. Which is change in B by AB. So change in AB, change in length of AB is 8.33101 to 10 power of minus 3 divided by AB's length is 15. So if I divide it, simplify it, I'll get epsilon AB, normal strain along the direction AB is 5.554 10 to the power of minus 4. So this is the normal strain along uh, direction AB. We have got. Next, we have to find out the average shear strain your engineering shear strain, whatever gamma xy we have to find out in 10 to power minus 2 radians. So basically, average shear strain gamma xy is this dou u by dou y plus dou v by dou x. So here we can see that u is 0.75, just taking the angles, and because the angles are small, tan theta is nearly equal to theta. I'm just taking the ratios directly. 0.75 divided by 20 plus 0.5 divided by 15. So if I sum this both average shear strain and engineering shear strain, be 0.070833 radians. This is the shear strain. But if I want to write this in a given format, which is into 10 to the power of minus 2 radians. So this is how we get the engineering shear strain or the average shear strain. So this is generally I have not taken the formula or something else. Basic intuition using the right angle triangle thing. I have calculated all the values of the strains. So if you have any doubt, please ask, or else start. I'll explain the various things from first whatever I have discussed today, because you were not present uh, during the initial first hour of the session. So first we have looked at this question where we have to find out what are the stresses which are zero at this point P, which is given when it is uniaxially loaded like this, and this is the fringe pattern uh, which we have got. So this is like a plate with a hole problem, and you can see a circular hole. So it is better to take a uh, what the coordinate system as a polar coordinate system, and in polar coordinate system the stress tensor will look like this: sigma r, sigma theta, sigma theta, and sigma theta theta, and this will be a element. If I take, stresses will look like this. So because this is a free boundary and it is not loaded free surface, so shear will not cross the free surface. That's why shear sigma r theta will be 0, and sigma rr also, because this is a free surface normal stress and it is not loaded. That's why this is also 0. Only we will have sigma theta theta, which is a non-negative thing. So this is the first thing, and then we are looking at this loaded element, and we have this is the uh, fringe pattern for this loaded element, and we have to find out the points at which the stress tensor is 0. So stress tensor is 0. Basically, if we look at this picture, whenever you can see dark spots, like dark black spots uh, can directly tell like from intuition that this is the stress tensor is 0 at those corners. So A, C, D, F, G, and I, J, L. So at this points, uh, normal stresses will be 0 and also the shear stress will be 0 because these are corners, and that's why uh, these all points have stress tensor as 0. And next, there is this special case which professor explained in the class. When there are corners like this, in the first case on the left hand side, uh, you can look at this point A, and here the stress tensor is 0 because this is there won't be any shear stress if you can see, and there won't be any normal stress, and the stress tensor is 0 here. But if you come to this point here, the stress tensor is not 0 because you cannot like take a element at this point, and you cannot say this normal is only this normal stress, and this you can say shear 0, but this may have there is a stress, but the stresses here are very high, and uh, like we cannot determine them at this corner, and that's why there will be a crack initiation, and through this crack propagates when load is applied. So that's why the stresses are singular. Singular means like very high stresses. So if you see the viscoelastic, photoelastic fringe pattern also, you can see very dark reddish uh, color here at this point. So this is a re-entrant corner, as professor explained in the class. Then we have a differential element of the material at a point which is subjected to a plane state of stress, plane state of strain, and for that uh, we have to find out uh, what is the first invariant. First invariant is basically, it is similar to what we have done in the last class, taking the sum of all the principal diagonal element, which is the first invariant, and it is minus 270. Then we go to the second invariant. Second invariant is basically taking the minus of the principal diagonal elements, basically taking the sum of all these submatrices, determinants of submatrices, and we get this as something like this. And then we go to find out the third invariant. Third invariant is the determinant of the matrix or the tensor which is given, and the third invariant is 0. And if we want to find out the principal strains, so principal strains is, can be found out basically by taking this determinant as 0, or you can say finding out the eigenvalues of the strain tensor. So I don't need to take this equation and individually write and simplify it again, because this is a simplified form when we know the invariants. So I have calculated the invariants. I'll substitute the values of the invariants in this equation, and if I solve this uh, equation, cubic equation, I'll get values of the eigenvalues are determined. So the highest eigenvalue of this is the maximum principal strain, and the lowest is the minimum principal strain. Here 158.64 is the max, and minus 428.64, which is on the negative uh, x-axis. We can say that is the minimum principal strain, and this zero is zero lies between this minus and the positive maximum and the minimum, and that you can say that is a uh, intermediate string. The next question which I have discussed here is, there is a displacement field given like this, and uh, xy are the coordinates, and basically these are in meters, and the normal stress, we have to find out the normal strain in micro strains in the x direction at point 1 comma 2. So if I so the displacement field, any displacement field, basically here the displacement field is given as d, but normally it is given as u bar like this. Displacement field is generally denoted by u, but here it is given as d. Uh, it can be decomposed into three components. So the displacement field along the x direction, y direction, and the z direction. So the component of displacement field along the x direction is denoted as u, and it is very consistent across different courses and texts, I guess. So, and in the course also we have followed this convention. Uh, Displacement component along the x direction is u, y is v, and z is w. So if I want to find out the normal stress along x, simply epsilon xx I can find out using this uh, uh, differentiation of u with respect to x, partial differentiation of u with respect to x. So this comes out like this, and then I have to find out the normal strain along y direction, which is found out by this differentiation of v with respect to partial differentiation of v with respect to y, and this comes out like this comes out as 4, and then I have to find out the value of engineering strain at the same point. So uh, so I am getting here 2y, and for the first point I am getting constant for any point. Epsilon xx is 1, and it is constant for every point, not just for 1 comma 2. And yy I am getting it as 2y for this point, because the y coordinate is 2, I am substituting y as 2 here. So epsilon yy I get as 4 microstrain, and then epsilon gamma xy. So basically I have uh, dou u by dou y plus dou v by dou x, and doing these differentiations of v and u and v with respect to y and x respectively, and substituting the value of x and y. So I'll get the value of engineering strain. So then after that I have to find out the normal strain as microstrain along 30 degrees to along the axis which is 30 degrees to the x-axis. So strain transformation law, I think stress transformation law also has been discussed, and strain transformation also looks like this. So when you are rotating the axis, you will get a transformation tensor, which is q, which is cos theta minus sin theta, and sin theta and cos theta. So using this is a transformation law. Basically you will get these expressions which were discussed in the class. If you simplify this also, the same expressions can be found out. So I have substituted the values which were given, and in the strain tensor, and we have found out whatever the values of strains in the transform coordinate, the rotated coordinate system. As I have said, uh, from the x-axis, the new x-axis is at 30 degrees. So x dash epsilon x dash we have found out as 4.348. That is the answer. And remaining stress components also for this transformed or rotated coordinate system are found out. And then the last question is trace of the rotation tensor of this displacement field. For any rotation, for any displacement field, if we take the displacement gradient, this is the displacement gradient. Just because we are referring to two-dimensional gases or plane strain gases in this course, I'm just removing the z components and taking the two-dimensional tensor. And this displacement tensor can be decomposed into two parts. One is the strain tensor and the rotation tensor. Basically, this is nothing but taking the if you have a matrix, you take you can write it in write it as a what you can say as a sum of any matrix can be written as a sum of symmetric matrix and a skew symmetric matrix. So I hope you have learned this in the linear algebra courses in your undergraduation. And this is the similarly we are doing this like decomposition for the displacement gradient, and if you do this decomposition, we'll get a rotation tensor and the strain tensor. So per rotation tensor, always the principal diagonal elements are zero. So some of these principal diagonal elements are anyway zero for any rotation tensor. That's why the answer of this question is zero. Lastly, we have discussed this problem where we are doing this change in length of side of rubber distorted, and we are finding out the normal strain and the shear strain on various directions. Okay, Kishore, have you understood, or I need to?
Yes, most of the I understood. I'm
Ah,
trying also to understand all of this, but definitely I am the employee of the company, so I didn't
okay,
getting that much time. But I'm trying to understand and listening the video also. So
okay.
yeah, that's why I'm not able to taking getting the time to uh, do all the session. But I'm trying to learn. I mean, watch the video with the proper justification. Those videos are already uploaded in the our course.
Okay.
Can you explain one thing? How to this frame the sensor?
How to place the sensor?
Sensor, yeah.
Oh, the thing I think you will. We are studying this in the coming week. Have you watched the lectures? This
Yes,
fifth.
yes.
Okay. So that thing professor will explain. I guess have you watched? Has he explained? Because I haven't watched the lectures. Uh, you were asking like how to place the sensor. Place the
Yeah.
sensor.
Political sector means, yeah, means this.
Uh,
Suppose the question in Quran means shared.
hmm,
Tau u upon tau y plus. So like that, the sensor. Can you scroll up?
yeah.
Just scroll up. Yeah, scroll up. Scroll up. Yeah. So suppose these are sensor. How to place and how means what is the correct position? How to
No.
reframe?
These are not. This you are saying that this is the sensor. Okay. This is
Okay.
not a sensor actually.
Uh-huh.
This is just I am taking an element, small element on the body. Okay.
Okay. Okay.
Strain tensors, you will find out like there are various strain rosettes, triangular rosette, T rosette. Have you watched these lectures?
Yes, I
Triangular
was currently on the 11th of the lecture number. Fourth week.
11th lecture.
Yeah.
Oh, fourth week. Okay. You are okay. You have watched the 11th lecture till the
Yeah.
11th lecture.
Till the video.
Okay. 12, 13, you have not watched, right?
Not yet. Yeah.
So if you look at the 15th lecture, uh, there is a lecture for the fifth week, which is strain measurement. In
Oh,
this, you will find out things are explained like how we measure the strain and all, strain rosettes and all.
okay. Okay. Thank you.
So, yeah. So if you just watch those lectures, because this the session which I am conducting right now is for the 4th week. So
Yeah, yeah,
I'm not
definitely. Got the
explaining this
point.
question.
Yes, yes,
Yeah.
yes.
Hmm.
Okay, okay,
So
thank you.
next week we'll look at those in detail, like whatever the things. Yeah.
Yeah, yeah, okay, yeah.
I apart from this, like what do you have any doubts from this? What I have explained, was it fast?
No, no, that is okay. Speed as is okay. I will also make a note from my side, and I will resolve the question and same like that has been uploaded for the tutorial.
Hmm.
Yeah, yeah, yeah,
Okay, okay.
yeah, yeah.
Okay, since we have time, I'll take another question, which is we have a displacement field like this. X square plus y I cap plus 3 plus z 3 plus z j cap plus x square plus 2y k into 10 power minus 6, and xy are given in meters. So first we have to write the uh, general representation of strain tensor. So this is the displacement field given. We have to find out the strain tensor for this displacement field. So strain tensor, I hope you have watched the lecture. Strain tensor is given like this: dou u by dou x, dou u by dou y. These are the dou v by dou y and dou w by dou z. And the remaining parts are given like this. Dou w by dou z. So this is a symmetric matrix. I don't need to write this. So this is basically epsilon xx, epsilon xy, epsilon xz, epsilon yx and epsilon xy, same thing, and yy, epsilon yz. Again, I'm writing this as a z. So this is the strain tensor epsilon xx. I have to find out given displacement field in this. This is u, this is v, and this is w. So U is epsilon xx is dou small u by dou x. U is x plus y square, x square plus y, right, dou x, get 2x. So I have to find out the strain at point at this point 1 3 1 and minus 2, 3 1 and minus 2. So this is 2 into 3 epsilon xx is 6. Then epsilon yy can write it as dou v by dou y. So v is here 3 plus z, and there are no y terms, and since it is partial differential equations, this is 0, and for every point this is 0. And if I take epsilon zz to w by dou z, so w is basically here x square plus 2y. I see, and all the z components are 0, so there is no z term here, so differentiation with z is 0. And I have xy, which is of dou u by dou y plus dou v by dou x. So u is x square plus y. So differentiation of u with respect to y will give me only 1, and v is v plus v, so this is 0. I'll get 1 by 2, and xz I can get dou u by dou z plus dou w by dou x. So u is x plus x square plus y. So this is 0, and w is x square plus 2y. So I'll get 2x. So I'll get x. So this is 3 x. So I'll get the strain tensor as first xx as 6, yy as 0, zz as 0, xy as 1 by 2, xz as 3, and xy xz I have to also find out uh, yz. Yz is basically y component with respect to z, and z component with respect to y. So v is 3 plus v, so get this one. 3 plus z differentiates with respect to z, get only 1. Though w is here x square plus 2y, so I'll get this as y. This is 3 by 2. So 3 by 2, 3 by 2, 3 by 2. This is the strain tensor which we are getting for this principal plane. Yeah. So this is how, if we have a displacement field, from this strain tensor is calculated like this. So displacement field is a vector, and the strain tensor is a, as the name suggests, it is a tensor. Tensor means nothing but a matrix. of certain dimensions. So we have done principal stresses using the Moore circle uh, concept. Moore circle we have seen in stresses. Similarly, Moore circle, there is also Moore circle for strains too. So I'll just explain how we go about drawing the Moore circle. So if you have an element like this and it has strains like this, and shear strains on XY. So it has to be not the engineering strain. So half of the engineering strain. So gamma XY is twice this tensorial shear strain. Yeah. So we have to be careful. So we have to take epsilon XY. So epsilon XX, first epsilon XX should be plotted, then epsilon YY. This is the normal strain axis, and this is the shear strain axis. Normal or shear strain axis. This is epsilon XX. This is epsilon YY. Similarly, because we have taken this epsilon XY, we have to take this in negative direction because we are taking an anti-clockwise moment. So generally this notation has been followed in the course. See, here also we'll follow the same. Clockwise notation, clockwise shear is taken as positive. Epsilon XY. Epsilon XY. We plot and we join both of these points. And taking this as the radius, we draw, this is the radius, we draw a circle like this. Looks like an ellipse, is looking like. So this is the major principal strain and this is the minor principal strain. And this is at an angle. Let's say this angle is 2 theta and the plane of principal stress will be at angle of theta from this plane. So in Moore circle it is 2 theta, but in general the plane is at an angle of 2 theta. Same thing like whatever we have done for drawing a Moore circle in stresses. Similar way we can draw the Moore circle for strains also to find out the maximum principal strain and the minimum principal strain. So here this is minimum principal strain, epsilon 1 and epsilon 2 are just same. So whenever we are looking at principal strains, these are principal stresses and principal strains. These concepts are very important because we want to find out these stresses so that we can design any component or any kind of element or like a beam or a bar or whatever you are designing, we want to make sure that the stress due to this the stress due to the applied load should not cause a maximum principal strain which is beyond the permissible tensile or the compressive strength or the shear strength of the material. So if this stress maximum principal stresses and maximum principal strains are more than the permissible limits of the material which we are taking, it will lead to failure and ultimately it will create a loss of property or life or whatever. Like if there are, if that is a building beam fails and what may happen. So we use this thing, use this stresses. So for maximum and minimum principal stresses and maximum shear stresses, and similarly the strains alternatively. These things are used for the design, safe and reliable design, and to make the structures whatever which we are designing the components, uh, uh, make them safer and take the load which has been applied on it without getting failed. And the concepts like shear strains and also shear stresses, uh, also this maximum principal stresses and principal strains which we are studying will be helpful when we go to the last part of the course. There are theories of failures which are discussed. Like there are different theories of failure which we consider for different material depending upon its properties. Like a brittle material, for brittle material there is a theory of failure which is considered. For ductile material there is a different theory of failure because they can fail differently. So using this principal stresses and principal strains, those were proposed, theories of failures were proposed, and using that there are many like structures are designed according to those theories of failures. This concept is very important in that way, principal stresses and principal strains, so that there is no uh, failure in any component or structure which we are designing, and it stays safe for any load which you apply. So you want to know the permissible load which you want to apply, and if you want to know if the structure is able to take that load whatever you are applying. So you have to say, you have to be like, if a building is designed for, if a building or a certain a machine is designed for a certain amount of load, you have to make sure that it doesn't cross. Like there is always like we use various factors of safety so that it doesn't go near to that also. uh, it remains very less. So while you design, you make sure that this takes uh, more load than what you expect, and while you apply the load also, you make sure that this load is lesser than what is permissible on the structure. So two sides of a coin we have to look, so that structure remains safe and the design is reliable and safe for whatever we are doing. So strength of material is basically we are discussing the deformations in the material. So engineering mechanics, I think you have studied that, deals with how rigid body motion is happening if there is a load or forces are applied in the structure. This is the deformation in the material. This course will deals with deformation in the material like distortion or elongation, whatever it is. and due to that, the stresses are developed in the material. Stress is nothing but the resistance, uh, which is caused due to the applied load. Yeah. So I think today we can close this session, and we will meet in the next session. If you have any doubts, you can ask me. Uh, Otherwise, I will just wind up today's session. Kishore, hope, are you there? Okay, okay, Kishore. I think you are not here. I'll just close today's session. See you in the next session, hopefully from the beginning. Yeah, thank you.